So an alternative form of the rate law is what we call the integrated rate laws. Now, integrated rate laws that we're going to look at are only going to be for the three specific cases that I have written out here: first order reactions, second order reactions, and zero order reactions. And we'll look at each of these in turn. One of the difficulties with the method of initial rates is that you have to do multiple experiments in order to determine the rate law. So we looked at this reaction where we had two reactants, and what we need are two experiments where we're varying our first reactant and keeping the second reactant constant, and then we need to do two experiments where we're changing the concentration of our second reactant while keeping the first one constant. So the minimum that we can do this in is 3 experiments. So that's quite a lot of work. We've got to do at least three experiments in order to determine the rate law. And we probably want to do a fourth one just to make certain that we haven't made an error. It turns out, though, that if you have a reaction that involves just a single reactant, and there are quite a lot of these, it is possible to do just the one experiment and determine the rate law. So if I have a reaction here, ozone, it gets degraded by UV light into oxygen and molecular oxygen, and what we would collect for this reaction is data of concentration against time, and unsurprisingly, the concentration of the ozone decreases with time. The rate law is going to look something like that, and what we want to know is what is the reaction order and what is the value of K. Because this is a reaction with just one reactant, it turns out we only need the one experiment. So here we go. Ozone is being decomposed in sunlight. Decomposition reactions only have the one reactant. We know that if this reaction was first order, then this is what its rate law would look like. And that would be equal to the negative of the change in concentration of O3 over the change in time. The coefficient here is 1, so we don't need that 1-on-1 term out the front there. Okay. So what we're going to do now is we're going to magically apply the rules of integration to this equation, and we're going to integrate both sides. And when we do that, we get this expression, which is what we call the integrated rate law for a first order process. Now, if you're interested in the math, the calculus that we use to do this, I've posted an explanation in the resources section and you can have a look at that. But what you'll see is that this is a linear equation of the form y equals ax plus b. And if we were to plot the log of the concentration of ozone against time, we should get a straight line with intercept being the original concentration of ozone and slope being minus K. So for a first order reaction where we only have one reactant, if we plot log of concentration against time, we will get a straight line, and that'll be a negative slope, and the slope will be equal to minus K. So we can get the rate constant and the order of reaction from a single plot. So in general terms, for a first order reaction with one reactant, the integrated rate law is going to be log of the concentration of our reactant at time t will be equal to minus KT plus log of the original concentration. And you can tell that a reaction with one reactant is first order because a plot of log of the concentration against time will give you a straight line with negative slope. The intercept of that line will be equal to the natural logarithm of the original concentration, and the slope will be equal to the negative of our rate constant. For a first order reaction, the rate constant will have units time to the -1. Okay, so here's an example problem. It says the following data was collected for the decomposition of N2O5. So we can see that it's a reaction that has only one reactant. So there's potential to use the expression that we just derived. And so then the first part of this problem says, is the reaction first order with respect to N2O5? Provide evidence for your answer. So what I need to do here is extend my table out to have a column that has the natural logarithm of the concentration of N2O5 in it, and then I'm going to plot this guy here against the time. And if that is a straight line with a negative slope, then I know that this reaction is first order. And when I do that, it is. The next thing that it asks is, what is the rate constant for this reaction? So what I've got to do now is I know that the slope equals minus k. So I'm going to have to calculate the slope of this line. So all I need to do is pick two convenient points. I picked 100 and 300 seconds. And calculate the slope between those points. So it is y step over x step. That gives me a negative number. So k is just going to be the negative of that slope. That's it written there in scientific notation. And remember, for a first order process, the units for the rate constant are going to be time to the -1, and our time unit in this case was seconds to the -1. So we are done. Okay. So something that kind of can be developed from the integrated rate law for a first order reaction is the concept of half-life. And so half-life is just a useful measure for how fast a reaction is occurring, and all it is the time for the concentration of a reactant to halve. So what we're really saying is that the concentration of our reactant at time t will be 1/2 of what it was at the beginning of the reaction, and that time t there is referred to as the half-life. So the concentration of A after a half-life will be 1/2 of the original concentration, and that's what I've written out over here. So now we put this expression for the concentration into the integrated rate law for a first order concentration, and we say that the natural logarithm of 1/2 of my original concentration will be equal to minus k times t1/2 plus the natural logarithm of my original concentration. So then I'm just going to kind of bring everything, I'm going to bring all of the concentration terms to the left-hand side, and that gives me this expression, log of 1/2 of my original concentration minus log of my original concentration. And I just want to point out now that there's a log rule that we're going to use now, and it says the log of A minus the log of B is equal to the log of A on B. So we're going to apply that at this point. So this term in here becomes the natural logarithm of the original concentration divided by 1/2 of the original concentration. So these terms are going to cancel out, and so I'm left with log of 1/1/2. Now, if you don't know, 1/1/2 is equal to 2. So now I'm just going to divide both sides by k, and what am I left with? Log 2 on k is equal to my half-life, and that is valid for any first order process for a reaction that has only one reactant. So for a first order process for a reaction that has only one reactant, the half-life is given by that expression there, t1/2 equals log 2 on k, And what's interesting about the half-life for a first order process is it doesn't change with time. So if I look at the time to go from 16 molecules to 8 molecules in this reaction, that's 1 second. If I look at the time to halve again and go from 8 molecules to 4 molecules, guess what? It's 1 second. And if I look at the time to go down to 2 molecules from 4 molecules, guess what? It's 1 second. So for a first order process, the half-life is independent of concentration. It doesn't change with time. And so sometimes it can be really easy to recognize that if you have your concentration of your thing over here and you have time here and you start off at 16, 8, 4, 2 and you get 1, 2, 3, 4, you might be able to recognize that because the half-life is staying constant at 1 second, without doing any math, you might be able to eyeball that this guy is first order. So if you recognize a constant half-life, then that's an indication that the reaction is first order. And sometimes you can use that to your advantage. Okay, so this is an example of doing that. So it says the following data was collected for the decomposition of N2O5. 2N2O5 goes to 2N2O4 plus O2, and we notice we have only the one reactant. The question then asks, is the reaction first order with respect to N2O5? Provide evidence for your answer. So what I could do is plot log of my concentration against time. It should have a negative slope, and then that slope would be equal to minus k. But before I head down that pathway, I'm going to see if I can, because I know that t and half is constant, I'm going to check for that. So let's have a look here, and what do I see? The concentration halves. And again, 500 to 0.025, it halves. 0.025 to 0.0, it's halving. So they've set this up so that you don't need to do the plot, that you can just eyeball it from here and see that as the half-life is constant at 100 seconds, the reaction must be first order. So you don't actually need to make the graph in this particular case. How am I then going to solve for what k is, because I don't have my slope now? Well, remember, t a half is log 2 on k, and if I reorganize, k is just log 2 on t a half, and so that's going to be log 2 on 100 seconds. So sometimes if they've given you a nice set of data where the concentration is halving again and again and again, you can avoid doing the plot in order to determine that this is first order. Now, that might not always be the case. All right, so let's have a look at this problem. It says the rate constant for the decomposition of N2O5 is 7.8 by 10 to the minus 3 per second. What is the half-life of N2O5? And the little trick here is that they've told you the order of the reaction because they gave you the units for the rate constant, and that immediately tells you that this reaction is first order. Because it's a decomposition reaction, that's where one thing falls apart, we immediately know that this is a reaction that has only one reactant. So now it's relatively straightforward. To get the half-life, I've just got to use the half-life formula for a first order reaction, which is the half-life is equal to log 2 on k, and sure enough, there it is. It takes 89 seconds to halve under those particular conditions. Okay, so we've done the section on integrated rate laws and half-lives for first order reactions. There'll be another 2 videos which explain how we might use these concepts for second order reactions and zero order reactions.